joint work with Thomas Dubos and my PhD student, Matthias. So adaptivity in numerical models, I'm interested in dynamical adaptivity where the grid resolution changes to guarantee uniform error or to focus on regions of interest. And it also makes optimal use of computational resources. So familiar ways to do this include grid nesting, unstructured grids. We saw an example of that, very nice example for sea ice, and structured grids. I'm going to propose using wavelets to do this because wavelets give you a general structure that can be used to make almost any method adaptive. Now, I've done this already in the case of engineering type flows. This is flow around a network of cylinders. I've also done it on the sphere, although at this stage I was kind of naive and I forgot about the need to conserve certain quantities. So the question is, can you have dynamic adaptivity using wavelets and still conserve mass and other important quantities? So in particular, can we make the Trisk scheme adaptive? So why choose wavelets? Well, wavelets were developed originally to analyze data. They're very good for data compression. In principle, you have a linear computational complexity, which is good for very large problems. They also have denoising properties. And with Marie Farge, we developed a method for simulating turbulence that's based on dividing turbulence into coherent and incoherent parts. And most importantly, wavelets is more a way of designing a multi-scale basis. It's a very general technique, and it can be custom designed for any particular manifold. The wavelets are constructed in the spatial domain. They form a collocation basis and can be adapted to a regular sampling. And you can vary the order of approximation. So one page that's a little bit mathematical sets the structure for a wavelet multi-resolution. Essentially, you have a sequence of approximation subspaces, which you can think of, for example, as just a set of nested grids. They're dense in L2, and each approximation subspace has a respaces of scaling functions. Scaling functions give you a smooth resolution, a smooth basis at a particular level of resolution. The wavelets span the complement, the orthogonal complement. In other words, they give you the detail when you move from a finer approximation subspace to a coarser space. And by measuring the detail, you decide whether you need to refine or not. In other words, that controls how you adapt your grid. Whoops, didn't want that. Come on, go away. Good. So you get, at a given level of approximation, you get a representation in terms of scaling functions, or you can get a representation in terms of the details at all different scales. And by filtering on the wavelet coefficients, you can determine whether you need a grid point or not. Okay, so the basic principle is you have a fine level of approximation here. You then want to go to a coarser level. You do an linear interpolation, for example, to predict this point. You get an error. That error is your wavelet coefficient, and you store that. But then you decide, well, I've now no longer conserved the mean of my function, so I take a linear combination of adjacent wavelet coefficients to correct these coarse points, and that's called a lifting. So the lifting conserves properties in your smooth approximation that you believe are important. So how do we turn this into a method to solve a PDE? Well, using this, you can approximate differential operators at a particular resolution. All of this in order n complexity. If we consider a front like this in one dimension, the significant coefficients, those wavelets above a certain threshold epsilon, are in blue here. So you notice that we need the small scale, so scale is in this direction, only very locally. Then to allow for the fact that our solution changes over one time step, we add neighbors at the same scale. That corresponds to a CFL criterion of 1. And we add neighbors at the scale twice as small. That accounts for steepening in a nonlinear equation, or de-aliasing, you might say. So how do we do this on the sphere? Well, on the sphere, it's the same idea. Here's a sphere. This is just two-dimensional sphere. It's a subdivision of an icosahedron. So we start with an icosahedron. We bisect the edges and project onto the sphere. We start with vertex values. We interpolate the points we've left out. We take the difference. That gives us our detail coefficients. Then we smooth, and that gives us our smooth and lift, and that gives us our coarser approximation. And we keep doing this each time, retaining the detail coefficients, the information we've lost, until we get to the coarsest representation. So we've got a restriction, which is the interpolation, and a high pass, the restriction to take us to the coarser level, a high pass filter, which is the detail, and we count the number of degrees of freedom. And this transform is invertible. And the key point here is each detail coefficient corresponds to a grid point. So if the detail coefficient at a certain point is small, that means we can safely neglect it to the tolerance we're interested in. So locally on the sphere, we would be looking at a neighborhood of points here. So the way this works is the blue points here are going to be the points that are on the coarse representation. The red points are what we leave out, and that's where the wavelet coefficients will live. So for example, if we consider this red point in the middle, we just do a linear we could do a linear interpolation, take the difference, that would give our wavelet coefficient here. But then we would have to lift these blue points because maybe we lose the mean of the function or some other property. And to do the lifting, we take a linear combination. We would lift this point by taking a linear combination of the neighboring red points. So the analysis from a fine scale to a coarse scale goes like this. We take the difference of the red points using a local interpolation. So in this case, the linear interpolation is very simple. And then we do the restriction. If we didn't do the lifting, the restriction would be we would just keep the blue points. But we have to correct the values, so we add in a linear combination of our wavelet coefficients. And the synthesis is going in the opposite direction from coarse to fine is just the opposite. So you have a forward and an inverse transform. So the key thing is working out what these stencils are, and the stencils are local. So here's our friend the Trisk scheme, which we saw this morning, and I'm just going to take this as given, forget about any defaults, assume it's absolutely perfect. The only thing that's not perfect about it is it's not adaptive. We would like this scheme to zoom in on regions of interest, and if we say we have a tolerance 10 minus 3, we only want to put those grid points that are necessary to achieve that tolerance. So I'll spend no time at all on the Trisk scheme, except to say there's two variants, one that conserves total energy and one that conserves entropy, and we decided to pick the one that conserves entropy. So what are the problems? Well, the problems are that we require different wavelet transforms for pressure and velocity. And the wavelet transform for velocity is a non-separable vector-valued wavelet transform, which is actually new. So we have to develop two distinct transforms. The grids are different on this sphere. The grids are, for pressure, our cells are hexagonal, and for velocity, we've got triangles. They're both non-Cartesian, and the hexagons are not nested when you go from one level to another. All of these things present technical challenges compared with the nice Cartesian case I've been used to in the past. Another challenge is that we're dynamically refining the pressure and velocity grids by looking at the wavelet coefficients of the pressure and the velocity. But what we really want to do is control the errors in the tendencies, dp by dt and du by dt. And those, the right-hand sides, involve both variables, u and p. And that means that we have to do some analysis to say, well, what should the tolerance be on the pressure and the velocity in order to control the tendency error? And that, again, is an extra complication from working on staggered grids. And on top of all that, we don't want to break the nice mimetic properties of the scheme. So we made life quite difficult for ourselves. This is what the refinement looks like for the grid. Here is a fine scale J, where the blue points are the pressure points, and we've got the arrows for velocity. If we go to a coarser scale, we would just end up with this pressure point and wavelet coefficients for pressure at these points here. So coarse value and wavelet coefficients. For velocity, we get these three coarse values plus a whole bunch of wavelet coefficients. There's 9, in fact, independent. So it becomes a little bit complicated, especially because the velocity transform is non-separable. But that's a basic structure. And the key idea to doing all this is to restrict the mass flux to conserve mass. So we don't restrict the pressure and the velocity independently, we restrict the mass flux. And this means that what we want to be able to say is that if we start with a quantity on a fine grid and then restrict and then apply the differential operator, we get the same thing as applying the differential operator on the fine grid and then restricting. In other words, this diagram must commute. So we have to ensure that certain discrete commutation properties hold under the application of restriction operators. And one of the key problems we had to solve was to find the correct restriction operators that preserve these discrete commutation properties. And here's just another way to look at it. Restriction of pressure commutes with divergence. Curl commutes with restriction of velocity, and so on for the Bernoulli function. And these are the physical properties that these relations ensure. Okay, so the conservative algorithm means that we take an inverse wavelet transform to compute scaling coefficients. So the scaling coefficients give us a basis at each scale. We compute the mass flux Bernoulli function by restriction, if we can, or by using trisc at the given scale. So why is that? Well, we believe that it's much better if we have the value at a finer scale, it's better to restrict it. If it doesn't exist, then we have to calculate it at the given scale. So that's the reason, again, for this commutation property. We need to be able to either restrict a quantity or compute it at the same scale. Similarly, for the potential vorticity flux, and then at each level independently, we just use trisc. So you can see that the adaptivity is built on top of an existing scheme. It's not actually, it doesn't modify the scheme itself, but you have to be able to restrict or prolong in appropriate ways. Okay, and then if you like thinking in terms of flowcharts, this is what we mean. At the finest scale, you don't have any choice. You can't restrict because there's no scale smaller. So you go from wavelet coefficients to scaling coefficients to fluxes, and then to tendencies, and then to wavelet coefficients of tendencies. But at an intermediate level, once you've got your pressure and velocity at that level, to find our fluxes, you either restrict, if those quantities are available from the finer grid, or you use the trisc scheme at level 1 in this case. So you choose whatever is more accurate. And here's just an example of the types of stencils. This is just a linear wavelet stencil. You take a linear interpolation and the difference, then you lift to conserve the mean, and then the complete restriction stencil looks something like that. So the stencils are a little bit big, but they're certainly finite. And there was a little bit, Thomas spent a long time fiddling around with diagrams in order to work out how you can write the restriction of a divergence as the divergence of a restriction in order to find a compatible restriction operator. So I'm not expecting you to see all these little arrows, but just to say that this decomposition, writing restriction of divergence as divergence of something, is what allows us to find the right restriction. Similarly, with velocity, you get a stencil that looks like this. And you're assuming constant circulation, linear interpolation and constant circulation. And you've got a natural curl-compatible restriction, which is just the average of the fine velocities over the coarse edges. Okay. So this is the scaling that you need in order to control the tendencies dp by dt and du by dt. And it turns out the scaling is slightly different in the inertia gravity regime and in the quasi-geostrophic regime. Essentially, if we want the threshold on pressure goes like the threshold on tendency to the 3/2 power. So this ensures that we have a relative error of epsilon, green epsilon, in the tendencies, and to do this, we need these two scalings. So the dependence on the tendency error is the same in both regimes, but we've got some extra parameters to ensure that both tendency errors have the same relative error. And that's important because remember, we're filtering the pressure and the velocity independently. So I cheated a little bit because I said we were solving this on the sphere. In fact, this is a prototype on the plane, but using the C grid on the plane. And we've been sure to design the scheme so that it works on the spheres. In other words, that it works on the 12 pentagonal points without any problem. But we thought to start out, it's easier to use a uniform grid. So what we did is develop a dynamically adaptive wavelet scheme for the staggered C grid on the plane. Conserves mass, and there's no spurious generation of potential vorticity, and it's compatible with the discrete topology on the sphere. So I'm just going to show you a couple of results. This is the linear inertia gravity wave. This is the adaptive grid, and you can see this is the level. Each number is a factor of 2, and the total grid, I think, was 4,096 squared. There's a little bit of noise, but it's not too much. But you can see that the grid follows the dynamics very clearly. Here's a nonlinear wave, and this is a zoom to show the steepening of the wavefront and the way the grid zooms in on the steep wavefront. Perhaps a more interesting case is turbulence. So here's an unstable initial condition that it will eventually form a turbulent flow, and here you can see the grid tracking the strong gradients and then becoming coarser again as dissipation smears out the potential vorticity. Yep, 5 minutes. We can check that we can control the pressure and velocity. So this is just saying pressure is error is proportional to epsilon. We can control the tendency error, which is important. And this is compression in the turbulence case. This is the number of grid points. And this is the overall compression compared with a uniform grid. And you can see that we go from about 50 times compression to about 300 times later, but that the CPU time per active grid point is the same. So that's important, which shows that it doesn't cost any more to have very compressed results. These figures just show the effect of changing the threshold. Effectively, increasing epsilon increases the dissipation. Skip over that. And you can define an effective Reynolds number based on this dissipation in order to gauge how turbulent the flow really is. So what's happening is that the adaptivity removes weakly energetic features at any scale. So that corresponds to a coarse graining, which is a form of dissipation. And this shows that this Reynolds number is proportional to 1 over epsilon. Okay. You win essentially because of adaptivity in terms of execution time. This is even on MATLAB. And I'll just move to the conclusions. So we're using spherical wavelets for adaptivity. It's a multi-scale representation. It's a mimetic discretization. And we have dynamic adaptivity controlled by a single local estimate, local error estimate. This is the error, the relative tendency error. Or you could define static grids. So we could just even more easily, in fact, define a static high-resolution region. And the adaptivity is an overlay on the existing Trisk discretization. We're currently working on a parallelized implementation on the sphere. Matthias is working at that right now and is close to getting results. Probably the first real application will be ocean simulations and then eventually a hydrostatic 3D extension and subgrid parameterization. Thank you very much. Question?
Do you need to store the coefficients, the wavelet coefficients? You store them everywhere at all times. So you are adaptive in how you use them, but not how you store them? Is that
No, they're stored adaptively as well. So a large part of the computational science problem is finding an efficient data structure to store the sparse wavelet coefficient information.
Okay.
So no, of course. Even in MATLAB, we just use the sparse data structures of MATLAB, which slows it down. But even then, we're not limited by memory. We're only storing the active coefficients.
Is it possible to apply your method to cube sphere?
In principle, I haven't looked at the details, but in principle, we should be able to do it. But that would involve designing different wavelet transforms. So the wavelet transforms here, custom designed for this particular grid, and also the particular conservation properties that we wanted. But the general principle of the method could extend to any discretization scheme, and I think more or less any grid.
So you never have to know the whole grid, right? You just really have to know that if I want to go to a new scale, I bisect my old scale, and then I need to figure out some way to keep track of parent-child association.
Yeah, so the nearest neighbors does it. So in fact, what you could do is start out with a coarse grid and an initial condition, and you can actually refine the grid to adapt, if it's an analytic initial condition, refine the grid to the initial condition. And the nearest neighbors are what you test. So after each time step, you test the neighbors in position and in scale to see if they're big. And if they're big, then you add them into the active grid and then add another neighbor. So I've got a nice example with Berger's equation with a steepening wavefront, and you can see the grid just zooms down to resolve the very small local scale.
So the tidy icosahedron is really only at scale 0. After that, it's just a bisection and projection.
Right. And one question is in terms of how stable that grid is when you go to many subdivisions. And so we might have to do something like go down 5 levels, move the grid points around to improve the grid before we continue doing the bisections. But for now, we're just saying edge bisection is good enough, and it just keeps going and going, or refining or coarsening as demanded by the dynamics.
Thank you very much.